A very good morning, dear friends. Today we are going to talk about demonstration of energy management in DC microgrid under the course title Smart Grid Basic to Advanced Technologies. Though some of the fundamentals we have discussed in the past, but today we will get into more details of this program, especially an application. In the previous module, we have seen the architecture of the DC microgrid and its grid integration. Further, we studied how to integrate a DC microgrid with the AC grid in that model. To understand the present module, energy management of DC microgrid, fellow students required the knowledge of the previous module. For this reason, we are repeating some critical aspects of the earlier module. Now, the module mainly focuses on energy management between DC and AC bus of the DC microgrid. This slide shows the block diagram of the L filter grid tied DC microgrid. In this slide, it is shown that the hardware test bed is developed by interconnecting various components. The AC side of the inverter is connected to the AC grid through L filter. The point PCC shown in the block diagram forms an AC bus where the AC loads are also connected. A Hall effect voltage and current sensor are used to measure the voltage and PCC and current through the inductor. The measured voltage and currents are biased to shift the signal above 0 level. The offsetted output of current and voltage sensors are given analog to digital converter, so called ADC pins of DSP launchpad TMS 320 F28379D. Inside the DSP controller, the ADC pins read the three-phase currents and voltages along with the DC link voltages. By using Clark's transformation, the three-phase voltages and currents are converted to the stationary reference frame from ABC to alpha beta, such as UABC to U alpha beta and IABC to I alpha beta. Further, the control logic generates modulation voltages for generating PWM pulses through EPWM pins of the DSP. These PWM pulses are used to switch the inverter. Now, the grid connected mode of operation. This slide shows the control logic used for interfacing the DC microgrid with the AC grid. The DC bus voltage controller regulates the DC bus voltage at the reference value and generates the AC power reference value. Active current reference is generated from AC power reference as the inner controller requires a current reference. The obtained AC current reference is converted to the stationary reference frame. This current reference is compared with the measured current, which normally gives an error. The error is processed through proportional plus resonant controllers for generating required modulation voltages. The modulation voltages are used for SPWM generation through EPWM pins of the DSP for switching converter switches, commonly IGBTs. The control variables of the PI controller as well as the PR controller can be obtained through proper tuning, ensuring that the stability margin should be more. Now, if you look at the laboratory prototype of the grid tied DC microgrid, This slide shows the block diagram of the hardware test bed. In this hardware test bed, the DC microgrid behavior is emulated through a power amplifier by configuring it with Opal RT. In the Opal RT, the DC microgrid is simulated, which contains PV, battery and variable DC loads. The scaled down DC bus voltages is given to be the analog input of the power amplifier. The current fed to this power amplifier is given to the analog input of the Opal RT. This creates a PHIL loop between the Opal RT and the power amplifier. The combined operation of the Opal RT and the power amplifier emulates the DC microgrid behavior completely. The behavior of the AC grid is mimicked through Synergia programmable grid emulator, semicron 3-phase IGBT based PWM inverter is used as a bidirectional DC-AC converter between the DC bus and the grid. The control logic shown in the previous slide is implemented in the DSP controller. The floating point Texas C2000 DSP controller of the TMS 320F28379 Delfino type is used in this hardware test bed. Now, moving to the hardware demonstration, let us have a look at the hardware test bed, and this test bed is developed by interconnecting various components such as grid emulator, DC microgrid is emulated through Opal RT, IGBT stack, filters, DC loads inside the Opal RT and AC load which is externally a bulb load. In this hardware test bed, the DC microgrid is emulated through the Opal RT, which forms a DC bus. The emulation of the DC microgrid will be shown in the later part of this video. This DC bus is connected to the DC input side of the IGBT stack. The AC side of the IGBT stack is connected to the input side of the MCB through an inductor. The output side of the MCB is connected to the grid emulator. The bulb is connected at the MCB point, which acts as a parallel AC load. Most of the components used in this hardware test bed have been explained in the previous module. In this hardware test bed demonstration, we are interested in showing how to program the desired control system in the DSP controller through MATLAB embedded coder will be explained in detail. Further, the emulation of the DC microgrid through the power amplifier by using Opal RT will also be explained. Finally, a test case demonstration shows the power exchange between AC bus to DC bus of the grid connected DC microgrid. DC microgrid emulation through power amplifier using Opal RT with the help of power hardware in loop experimentation, so called PHIL experimentation, the DC bus of the DC microgrid is emulated through a 4-quadrant power amplifier. The DC microgrid is implemented in the Opal RT, which runs on RTLab software by calling the MATLAB Simulink files. The DC microgrid consists of solar, BESS and variable DC load connected to a DC bus. This DC microgrid is initially simulated in the MATLAB. Now, the simulated DC microgrid is rearranged in the form of a master subsystem and control system. The master subsystem consists of power sources or control/computational algorithms. At the same time, the console subsystem consists of variables that need to vary in real time operation. To emulate the DC bus, voltage through power amplifier, the DC bus voltage is sent out through analog out of Opal RT by scaling down to 0 to 10 level, which is the power amplifier analog input voltage level. The power amplifier is configured to external mode, which gives the voltage corresponding to the analog input voltage value. Now, the analog output of the power amplifier is given back to the analog input to the Opal RT controller. This input signal is the input to a current source connected at the DC of the DC microgrid. Here, the analog output of the power amplifier is the current signal that either fits or draws from the power amplifier. The same current signal is either fed or drawn through a current source at the DC bus of the DC microgrid inside the RT lab of the Opal RT. This looping system between Opal RT and the power amplifier effectively emulates the DC bus of the DC microgrid. The output of the power amplifier is connected to the IGBT stack at the DC input side. The output side of the IGBT stack is connected to MCB, which forms an AC bus at which the AC load is connected parallel to the grid. Here, the AC load is a bulb load and the IGBT stack acts as an interface between the AC grid and the DC bus, which is called an interfacing converter. The control system of the IGBT stack is implemented in the DSP controller. Implementation of the control system in the DSP controller as follows. The voltage and current measurement are given to the DSP controller by using biasing circuits. The accessing of ADC and PWM pins of the DSP controller is explained in detail in the previous module. In this module, we are very much interested in showing the implementation of the control system within the DSP controller. Initially, the grid tied DC microgrid is simulated in the Simulink and the corresponding control is implemented in the same Simulink. Make sure that this simulation should run perfectly. After simulation, remove the plant and keep the control system that is required in DSP. Configure the DSP launchpad at the hardware setting of the Simulink setting pane. Before configuring the launchpad type, ensure that the required softwares are needed to be installed in the system as per the guidelines given by MathWorks. After the configuration, the ADC pins must be configured to get physical signals into the DSP controller. Make sure that the ADC pin configured inside the Simulink is the same as the pin the signal needs to connect. The control system process the signals and generate modulation signals, which are used to generate PWM signals. These PWM pins need to be configured to take out from the DSP board. Now, moving to the hardware demonstration test cases, we will consider the first case. As we know, the DC microgrid is emulated through the power amplifier, and the control system of the interfacing converter, which is between the AC grid and the DC microgrid, is implemented in the DSP controller. In this test bed, the interfacing converter has been given the responsibility of controlling the DC bus voltage, which is at 400 volts. The first test case that we need to observe here is if the sum of the power generated by the PV and BSS is more than the DC bus load, the power flow from the DC bus to the AC grid, and to achieve the above two phenomena and to demonstrate this test case, we assumed that the power generated by PV and BSS are constant and the DC load is varied in steps. By looking at DSO, we can clearly witness that the decrease in DC loads increases the current magnitude. Looking at the power amplifier power sign, which is positive, means the power is flowing from the DC bus to the AC grid. Now, moving to the second test case, similar to the previous test case, the power generated by PV and BSS is less than the DC load connected at the DC bus. By looking at the DSO, we can observe the increase in the DC load reflects the current magnitude. Looking at the power amplifier power sign, which is negative, means the power is flowing from the AC grid to the DC bus. So, earlier it was DC to AC grid and now it is AC grid to DC bus. The DC bus voltage is always regulated to 400 volts. From these test cases, we have witnessed the energy exchange between the AC grid and DC microgrid. Now, moving to the references, all the test material which has been presented before you, we have referred the following references very closely. However, I also suggest you to refer important textbooks and many more references for your kind consideration. To conclude, we have experienced how to use a DSP controller in applications of grid integration of renewable energy sources and DC microgrid, etc. The significant benefit of this lecture is that the students can develop their own control system to control a DC microgrid with low cost controllers like DSP controllers. With this, we are coming to an end of today's lecture. Thank you for your kind attention. Thank you.